Sir, Sri, sir, good evening, sir.
Sir, good evening, sir.
Good evening, sir. Just we wait for 2 more minutes, sir. 1 or 2 minutes.
ఓకే సార్.
పార్టిసిపెంట్స్ ఇంకొంతమంది రానివ్వండి సార్, స్టార్ట్ చేస్తాము.
అలాగే సార్. నేను ప్రెజెంటేషన్లోకి వెళ్ళిపోమంటారు సార్ స్క్రీన్కి.
స్క్రీన్ పెట్టండి సార్.
ఓకే సార్. I will start presentation. I will wait for a few minutes and then I will start the talk.
ఓకే 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 సార్.
Thank you. Lecture series. Voice. మామూలు వాటర్. Sir, very good evening to all the faculty members. I'm very thankful for the Dean CRI for arranging this lecture series. Thank you very much, Yoganathan sir and Peter sir. And for the sir, am I audible, sir?
Yes, sir. Voice is
Okay,
clear,
sir.
sir.
Yes, sir. So today I'm going to explain briefly about the NASA Open VSP, that is the Vehicle Sketchpad software to analyze the aircraft after designing the aircraft by the request of the proposer. Generally, the request of the proposal will be received from the customer. Okay. After receiving the details from the customer, the general details of the request of the proposal of an aircraft are the takeoff distance and the landing distance, what is the payload, and what are the ammunitions, what are the missions of that aircraft, what are the phases, how many nautical miles it has to travel, any ammunitions are there, then what is the payload. There are so many factors will be considered in the request of proposal. So how much of gravity it has to overcome in different phases, like that. So for that purpose, we will make use of the softwares that is given by Jock D. Mettingley, who is working till today with US Air Force, and he is the first designer, especially for the combat vehicles. So after designing the aircraft, we need to design the various components of the aircraft. So after designing, we need to analyze that aircraft. So once the aircraft is designed, we need to go for the analysis of the aircraft under the various conditions. So now we are taking the second part. After designing, we are preparing the model and we are analyzing the aircraft design using parametric geometry tools. So for modeling and for analyzing, we are making use of NASA's aircraft design software. So now I am explaining about this. The purpose of the project, especially this presentation, is to give an idea about the usage of this vehicle sketchpad, this VSP, as an analysis tool for computing the lift and the drag coefficients under varying flight conditions using several models. The various flight conditions will be accelerate, climb, and so next there are different phases are there. So here after climbing, what is the subsonic cruise climb and patrolling, subsonic penetration, delivery expendables, that is the reaching to the subsonic supersonic penetration to the escape dash, climb, subsonic cruise climb, descent, and then finally landing. There are so many flight conditions are there. So for all these flight conditions, what is the position of the flaps, especially the aeronails, and for respective aerofoil sections, what are the coefficient of the lift and the coefficient of the drag? These are the important parameters we need to analyze. Using these values, we are going to plot a drag polar versus lift versus drag curves. Okay, next. Here we are going to discuss about the modeling with open VSP, that is vehicle sketchpad, X file, the designing of the aerofoil shape, wings, horizontal stabilizers, vertical stabilizer, and aeronails, etc. And VSP aero is used for analysis for different flight conditions and for animation also. Okay. Next. So modeling with open VSP, we can design these models. The aircraft shape will be like this. So generally, I will like to explain briefly. These are the wings. Okay. So here in this portion, this we call it as the aeronails, and this is the vertical stabilizer, and this is the horizontal stabilizers. We call this as the propellers. Will be like this. Okay, these are the propellers here. This is being provided here, and this. Okay, this one is also the horizontal stabilizer. This itself is the vertical stabilizer. For this is provided here. This is about the brief terminology about this one. Next. So modeling with the open VSP. It is a parametric aircraft geometry tool which allows the creation of 3D model of an aircraft defined by common engineering parameters. So in the early 1990s, the open VSP has been developed and it is introduced by the NASA. And the next one is the modeling with open VSP. Modeling with the open VSP. This one. There are two basic shapes that determine almost all the aircraft components are the fuselage and the MS wing. The other components may be for more complex aircraft geometries, but may not be used for VSP aero analysis. For analysis, first we need to create the geometry. That geometry will be created using Open VSP. Okay, so let us see the software, that is the Open VSP. This is the Open VSP software. Here I will explain briefly how to create this. This is the software Open VSP version 3.2.41, and here I am loading this file. Let me wait for a few more minutes so that you will get this file. Here I am making use of this basic geometry, especially. Right. So the basic components are the fuselage. This will be the fuselage. There you can create it easily by specifying the what is the length and what is the diameter at each section, and you can alter the position of this component of this X form, and you can select the material for this under this custom settings. So what is the X section, cross section at this level? What is the height, width at each cross section? You can select what is the shape of this geometry. See, now we are selecting at a particular location. Okay. See, for this section 2 will be this one. Section 3 for this. So among these, what is its radius and its what width, height, and everything will be selected like this. Okay. So this is about the fuselage, and here you can select this position. What is the location? You can alter the location of this. I will change the location of this. You can alter the location of this, the fuselage especially for this one, or you can change the location of the Y, and you can change the location of the jet. You see this part. Okay, like this you can arrange and you can orient, and you can rotate this along X, Y, and Z directions. You can move the component, and you can align this with the rest of the components, with the wings, landing gates, and with the engine, especially the propellers, and everything will be designed and will be arranged as per the geometry requirements. Okay. See, after this, you can prepare this X section. So at each location, what is this position? That is very important. At the fourth location, let us see what is the shape of this one, especially at this X section. Okay. So at this particular section, you can specify what is the width and what is the height, or the if it is a circular one or if it is an elliptical one, whatever it may be, you can specify it clearly. Okay. So this is about the fuselage. Next, coming to the main wing, the horizontal stabilizer. So this horizontal stabilizer also will be same thing. If you want, you can modify this. Its wing length, and you can change the blend on the aerofoil shape. What is the aerofoil shape at each location? At location 4, let us say for this example, these are the 4 locations are there. In these locations, and this one. Okay, let us forget about this one up to here. Like this, each component will be created with an user-friendly variables so that you can design this aircraft according to the given dimensions very easily. So after this, let us go for the presentation now. This one, next page down. So like this, when you change the cross section at this particular section, the size will be varied like this. Now I will change the cross section at this section so that this normal representation will be changed to the desired representation. Okay, what is the front end and what is the rear end of this vehicle? What should be the diameter or the rectangle? What is the shape of the cross section at each location? You can specify it clearly using this software. So after this, we will go for the wing. The wing will be primarily like this, and you can change the parameters and you can bring it back to this shape. Okay. Sir, is the presentation is visible, sir?
Yes, sir. Visible, sir.
Okay. See, if I enlarge it, I cannot use some features, sir. That's why I'm not enlarging. I'll start thinking here. So here, after modification of this aerofoil section, if you observe this section, the aerofoil section will be like this. Okay. So we will change this length of this section and we can change this width like this so that you can bring the shape to this manner and you can change the span of this entire thing and you can specify the cross-sectional area, sorry, span area so that you can design this. See, or if you have any front view, top view, and the side view of the model or any scaled model also, you can design it by matching with this front view, top view, and side view. You can design this. After this, you can change the parameters considerably. You can alter the entire geometry according to the respective scale. Next one, like this, with that VSP, you can design the various components. This will be like this. This is the actual model. This is the actual flight. So when this is modeled, it will be in this manner. This is the actual one. When you create this in VSP also you can do all this mirroring, everything. There is a glass, mirrors, and everything will coloring, everything will be done. For the, once you design it, and when you import into analysis software, this will look like this, or like this. All this will be in this manner. Okay. Next one is how to do this, making this open VSP. Okay. Next, while doing this model, a care must be taken in order to avoid the crashing of this model when it is imported into the analysis package. So that is the avoid clay modeling, especially. So clay modeling, avoid clay modeling. That means you should not stretch too much or pull until the model matches the diagram. Just ఏదో match కావాలని try చేయకూడదు. So you should give clearly the relationship between the parent and the child component, and there should be a perfect relationship, and there should be no relative movement between the two components. And that's location and the dimensions will be specified clearly. Otherwise, it becomes a some vacant will be provided, so that will leads to the failure of the mesh in that location, during the computation while solving the equations, so the solver will get crash. So that means you should not leave any open components. The geometry analysis tools will crash the program especially. This is already we discussed. Start and finish the physiology to object with the points. Whenever you start the physiology, that should be started with the point and should be ended with the point. So this is the point and this is the end point for the physiology. For any physiology. So here is the compartments. Here we will get the wings. So whenever you start this physiology, you should be started with the points and end with the point only. Here the circular or elliptical geometry or maybe rectangular geometry, whatever it may be, the required. Okay. And especially while designing this, we should keep the backup files, especially. Even if you make simple mistake, when you should not modify it, if you are not in a position not to modify it, then the original diagram will be wasted. We have to start from the beginning itself. Instead of doing like this, once you prepare a perfect model, then you have to save that model up to that level and keep some backup file. So this further information regarding this open VSP modeling, you can go to this site. Next, coming to the X file. What is this X file? You may get some doubt here. So this X file, if you observe this geometry, this is the aerofoil shape. This is the aerofoil shape. If you observe this shape or section, this is the aerofoil shape. Okay. So this aerofoil shape will be in this manner. So when you take this aerofoil, X and Y position, each point we have some nodes. We have to write this data file, X and Y files, one data file which contains X and Y coordinates of all nodes. These are the nodes. Okay. So these nodes will be represented. So once these nodes will be represented, this will be imported into the X file one-dimensional X file one-dimensional software. Let me explain. This X file software where it makes use of that geometry coordinates, especially for finding out the lift and the drag coefficients for the subsonic aerofoils. For the subsonic aerofoils. So observe here, this X file is a software that is especially used to find out the coefficient of the lift and the coefficient of the drag for various cross sections of the aerofoils. So the flow conditions you have to define in the initial and the boundary conditions. You can use this X file software for the viscous flow or maybe for inviscid flow. So considering the viscosity or neglecting the viscosity, you can do the analysis for the existing aerofoil, allowing forced or free transition. Okay, it may be a force or maybe a free transition. So, and translation separation bubbles will be considered. Limiting tiling edge separation. What is the separation of the flow at the tiling edge? Okay, that will also be determined. And the lift drag predictions and maximum quotient of the lift will be determined. And these will be utilized in this Karman T Seaman compressibility correction. And this may be a fixed or varying Reynolds number. So what is this Reynolds number? So when you have this geometry You have all these nodes will be specified. What is this angle of attack for this air flow? That will be specified. That is alpha. And next thing is, what is the Reynolds number? Velocity of the flow is equal to how much? And whether it is viscous or not. Okay, that will be specified here. Viscosity. So for all these conditions, we will make use of this software to find the coefficient of lift and the drag and will be plotted suitably. And especially for this aerofoil, the minimum width that should be taken for this aerofoil section is 3 feet. Otherwise, so that geometry is not sufficient to find the quotient of the lift and the drag. So for finding out the quotient of the lift and the drag, so generally there are two methods will be make use of. One is the mapping formulation method. Another one is the basic panel method. There are two methods will be provided. Okay, using these two methodologies, we can find out the quotient of the lift and the drag. Next. So this is already explained. This X-foil is primarily used to collect the profile drag data under various under various flight conditions. Where it may be a maximum cruise or best endurance cruise, best climb, and high lift scenarios. And these are nothing but the mission phases. So this will be provided in the request of proposal itself. The request of proposal will be given by the customer. So this will be generally the standard profiles of NACA 65 with 415 nodes, and this is 415 nodes with a flap. This will be like this, and this is the flap. What is this flap? The function of the flap is to get a high lift, especially during the takeoff and during the landing. So when the flap is applied at a different flaps, what is the coefficient of the lifts and the coefficient of the drag? That you need to determine. So once this is determined, so then you can prepare the control strategy during the takeoff and during the landing, how to take off the vehicle and how to land the vehicle. These details will be provided submitted in the form of an lookup tables to the VSP Aero software. That is another one. So this is the output from the X-foil for the different angles of attacks. What is the quotient of the leg and what is the quotient of the drag and what is the delta pressure variation, that is the pressure gradient at different conditions. Okay, and this data will be provided, and this is used as a drag build-up worksheet, and this will be exported to the VSP Aero software especially. Next, this is the when you plot this will be in this manner. For the different conditions, the plots will be plotted here. So the time is not sufficient for me. So how to obtain this one? Next. So using this X-file, so there is a sequence of series, how to run this software and how to export this data into the VSP Aero. So this sequence of steps will be provided, and here at each stages we will provide what is the angle of attack and what is the Reynolds number, Mach number, and enter the CLC required for steady flight. Like that, we will provide this one. And the output file may be the Excel file or maybe a dot file, .dat file that will be created. The next one is the VSP Aero. So this is the fast vertex lattice analysis tool for VSP degenerate geometry files. VSP degenerate geometry files. Sir, I think time is over now, I think. Shall I continue,
Sir,
sir?
sir, you continue, sir.
Yes, sir. So I will quickly continue. And so this one is a free vertex software, and this is also given by the NASA's open source software. Okay. So this software contains integrated actuated disks that can be accurately described, especially for fast and easy aeropropulsive analysis. So after designing the aircraft, we are finding out the question of the lift and the drag conditions for the different aerofoils that will be loaded into the VSP aero. After this, we will, in the VSP itself, we will degenerate the geometry. That degeneration is very important. So if we want, you can separate this fuselage and we can study only the wings and the horizontal stabilizers in order to reduce the computational effect. Okay, so that will be done there, or otherwise you can go for the full geometry depending upon the computational resources that are being available. If you are making use of the supercomputer, then you can go for the full geometry also. Even with that also, it will take nearly 2 to 3 days to compute the full geometry analysis. So next, we can make use of the open source software that will be released here. And next, I will quickly realize this one. And so we are specifying the actuators. That means once the flight is being designed and the geometry is being exported to the VSP aero, in the VSP aero, we will describe the flight scenario. What is the takeoff distance? Okay. Next, what is the position of the aeronoils? That is the takeoff strategy. You have to specify. Acceleration strategy. You have to specify. So for this, you have to specify the rotor dimensions and its speed and what are the flap conditions. This one. So after this, once you specify this and solve this for the initial and the boundary conditions, an animation of the aircraft will be visible in the side window, taking the it is taking the takeoff and the steady flights conditions. That means you have to describe the every phase. So what is your mission and what are its phases? Phase 1, phase 2, phase 3 like this. For example, the phase 1 is the warm up and the takeoff. Next, accelerate and climb, supersonic cruise climb, and descent, and combat and patrolling, supersonic penetration. Like this, there will be much more things will be there. So just after the once these conditions will be achieved, then once the all the phases of the mission is being accomplished, once the design is satisfied with all the mission phase conditions, then we will go for the actual production. So before going to the actual production, now the geometry will be given exported to the ProE or SolidWorks. There actually the internal details of all the components will be given and its assembly will be prepared so that each and individually a detailed component geometry will be designed thereafter only. So sorry for delaying. This will be taking few more hours also. I'm stopping here after giving this analysis. So thank you for
Thank you,
providing this
sir.
opportunity, sir. So
Okay,
any
sir.
doubts
Continue.
regarding this, so you can contact me or you can ask me any doubts regarding.
Sir, any queries you can ask, sir. Ask to Srihari, sir.
Yes, sir. It is an open source software, sir, but you have to understand thoroughly before going to use it. So there is two textbooks are there. That is aircraft design and aircraft structural analysis. That is written by Jock D. Mattingly. So he is a professor in the University of Washington, and he is also a member in the U.S. Air Force Academy. So he is providing the open source softwares, the AED software, that is the aircraft engine design software, that will be used to analyze the aircraft after the request of proposal is being read. It may be passenger vehicle, or it may be camera vehicle, or it may be petroleum vehicle. What kind of the vehicle we need to design, and what are its missions, and what are its landing distance, especially should be provided in the request of proposal.
Okay, sir. Thank you, sir.
Thank you,
Thanks
sir. Thank you
for
for
sharing knowledge.
giving the opportunity, sir.
Thanks for sharing
Thanks
knowledge
for
with
the
us, sir.
CRT. Yes, sir.
Okay. So I thanks all the participants.
I
For,
request all the participants, sorry, I will thank you very much for all the participants for listening patiently. Thank you very much for the KSRM, CRA faculty, and for the principal and the director, and for the management members also. Thank you, sir. Thank you very much.
thank you.
Can I close the session, sir?
Yes, yes, sir.
So for the
So
further any, if you want, anybody wants to proceed in this direction, you can contact me. I will share the software files also. Thank you, sir. Thank you very much.
okay, sir. Thank you, sir. So with this, we end the session. So again, we meet tomorrow at the same time. Thank you, and all.